Hello physics enthusiasts. Today I want to report a little breakthrough from my experiment. After now building up the experiment for years and having several trials of getting some fluorescence light out of it, I now can report that I managed to get europium fluorescence at cryogenic temperatures, exactly at around 10 Kelvin. I measured a spectral line of a few europium atoms. And this is a little breakthrough and the beginning now of a bigger measurement series for my PhD thesis. To explain what I measured, basically one can summarize this in this one graph where you see a spectral line of one transition of these europium atoms. What I was doing is taking my laser and sweeping slowly step by step for each blue data point, changing the color of the laser light. And then I was recording, this is the y-axis here, you can see I was recording the count rate of the fluorescence signal on my detector. So I placed my camera, basically a camera, behind my experiment and collected the fluorescence light from the europium atoms. And you see that for a certain color or within a certain small color range, you see an increase of the fluorescence rate, and this is when you exactly hit the color of this europium transition. This is already a proof of quantum physics of discrete energy levels in an atom, which is not explainable by classical physics. So it's quite astonishing, this kind of simple measurement, but it gives you a lot of insight of the quantum world actually. To get a better understanding of what happened and how I performed this experiment, I just did an easy drawing of basically what's happening inside the europium atoms. So I have these two energy levels, E1 and E2, which is two different shells of the europium atom. And there the electrons reside. So here this is the ground level where usually the electron just sits in if basically no light is shown onto the europium atoms. Now I take my laser and switch it on, and if I hit the right color, that is the right wavelength of the light, I can excite this electron onto the upper level E2. And then after some while I switch off my laser, wait for about 1 millisecond, and then this electron falls down into the ground state again on its own, it creates a photon, which we call then the fluorescence. So it sends out light of the same color again, which is then the fluorescence light that I can measure. In this process, of course, I repeat thousands of times in order to create such a graph. And the astonishing thing is really that this is a proof of quantum mechanics because we get only this fluorescence light in a narrow spectral window, we say, just for a certain range of colors that the laser has, we can excite and do this process inside the atom. This means we have discrete energy levels, we have a discretization of matter basically. And this is not explainable with classical physics, because in classical physics what you would expect is a continuous distribution of these energy levels, so there's no fixed energy gap, but it's just continuous. So you can take every color and get this fluorescence light out of it. So this graph in classical physics would just be a straight line, so you can get out the same fluorescence light with each color. But this is not the case, as we see here the proof. So this is really a quantum mechanics behavior, and that's why we call the field that I'm working in quantum optics.